So good afternoon everybody. So in this class we prove another theorem on normal subgroups. So it states that if n is a normal subgroup of a group G and H is any other subgroup of G, then NH is a subgroup of G. NH is a subgroup of G. Okay. So this is the statement of the theorem. Here what is given? N is a normal subgroup of G and H is any subgroup of G. H is a simple subgroup of G. Then NH is a subgroup of G. This we have to prove. To show that any set is a subgroup, we prove one condition. That is what? Suppose that if we want to show that H is any set, if we want to show that, say H is a, if we want to prove H is a subgroup of G, then what we have to show? We show that for all x comma y belongs to H, xy inverse belongs to H. If this is proved, then this implies H is a subgroup of G. Okay, so there is one theorem on this. It's okay. So a subgroup, a set H of a group G, a subset H of a group G is said is a subgroup if and only if xy inverse belongs to H for all xy belongs to H. Okay, so if you proved this one, then it implies H is a subgroup of G. So okay, so that only we are doing now. So to prove what we do, we take let the set NH is equal to, it is of the form small nh, where n belongs to capital N and H belongs to capital H. Now as n is a normal subgroup, okay, n is a normal subgroup, then when n is a normal subgroup means what? N is also a subgroup. When n is also a subgroup, then n is a group also. Okay, n is a group also. When n is a group, then only it can be a subgroup. When it is a subgroup, then only it can be a normal subgroup. So therefore, so n is a normal subgroup. So it means that n is a group. So n is a group means there exists an identity element. So therefore, let E belongs to n, and H is also subgroup. H is a subgroup. So subgroup also contains identity element. So let E also belongs to H also. Okay. So this means when E belongs to N and E belongs to H, then E also belongs to NH. E also belongs to NH. Okay, so which implies the set NH is not equal to 5. The set NH is not equal to 5 means it contains at least the identity element. NH is not an empty set. NH is not an empty set. So at least it contains what? The identity element E belongs to NH. Okay, so now what we do? We consider let x comma y belongs to NH. X comma y belongs to NH be two arbitrary elements. Okay, so then therefore x is of the form n1 h1 because x belongs to capital N H. So x is of the form n1 h1 and y is of the form n2 h2 for n1 comma n2 belongs to n and h1 comma h2 belongs to capital H. Okay, so now we prove xy inverse belongs to H. We prove xy inverse belongs to H. Now consider xy inverse is equal to, so x means this is x, n1 h1, this is x, then y means n2 h2, so n2 h2 whole inverse, so which is equal to, which can be simplified as n1 h1, then bring this h2 here, so it is h2 inverse n2 inverse, or which is equal to n1 into, group this h1 h2 inverse, then n2 inverse. Now since h1 and h2 inverse is a third element, let h1 and h2 inverse be h3, so then this becomes n into h3 into n2 inverse, or which is equal to n into h3 into n2 inverse into, this can be written as h3 inverse into h3, because any element with its inverse gives the identity element E. So if it is E, so E can be written as h3 inverse into h3, or which is equal to n h3 n2 inverse, then combine this h3 inverse here, so h3 inverse into h3, or n n2 inverse, group this h3 and h3 inverse, h3 inverse into h3. Okay, so or otherwise this can be written as n, then this first you take h3, then n2 inverse, then h3 inverse dot h3. You can take in this way. Okay, first is, this is n, then here just rearrange these terms, so take first h3, then n2 inverse, then h3 inverse, then third h3, so now as h3 n2 inverse and h3 inverse belongs to capital N, because N is a normal subgroup, so therefore this belongs to N, okay, so therefore let h3 n2 inverse and h3 inverse is equal to n3, let it be some element n3, so then this equation becomes, therefore xy inverse, so this we have taken xy inverse is equal to, so now here this is n, and this is n3, and then h3. Okay, so this is n3, and this one is, sorry, here it is n1, no, okay, n1, it is n1, make it as n1 here, so n1, and it is n1, n3, h3. So now taking n1, n3 is equal to n4, so replacing that we will get n4 into h3, so which belongs to nh, which implies, and this belongs to nh, and this is equal to xy inverse, it means that xy inverse belongs to nh, so therefore nh is a subgroup of G. NH is a subgroup of G. In the same way, we take another theorem, that is on center of a group. Theorem 5. So it states that the center Z of a group G is the set of those elements of G which commute with every element of G. So here the theorem is the center Z of a group G is a normal subgroup. So here the statement is the center Z of a group G is a normal subgroup. So you have to show that center of a group G is a normal subgroup. That's all. Okay, so now here actually what is the center Z? The center Z of a group G is the set of those elements of Z which commute with every element of G. Commute with every element of G means what? So it holds the commutative property with every element of G. Okay, the center group G is a set of elements of G. Suppose that if G is equal to 1, 2, 3, 4, 5, 6 and so on. Okay, then Z is equal to what? Z of a group G is the set of those elements of G which commute with every element of G. Suppose that Z is equal to, if I take 3, so now I commute with this 3 into 2. So 3 into 2 is equal to what? 2 into 3. If 3 into 2 is equal to 2 into 3, then Z contains that element. 3 into 2 is equal to 2 into 3, means both are equal to 6. So therefore the Z element contains that element 3. Similarly take the element 4. Then 4 into 2, then 2 into 4, both are equal to 8. So therefore 4 belongs to Z element. Right? So similarly if you take 5, so 5 into 3 is equal to 3 into 5. So both are equal, 15. So commutative property holds. So 5 also comes under this set Z. So like that, if you consider one element, say 3, if you consider one element, so it should commute with every element of G. So 3 into 1 is equal to 1 into 3. Then 3 comes under this group. Then again 3 into 2, 2 into 3, both are equal. So again this 3 comes under this one. 3 into 3 and 3 into 3 both are same. 3 into 4, 4 into 3 both are same. Therefore 3 comes under this section. So like that, if you take any elements, the elements which commute with each and every element of G, it is a group of that elements. Okay, so Z is equal to a center of group G means what? It is a set of those elements of G which commute with every element of G. Okay, so now we have to show that this is also a normal subgroup. So now proof. How do you prove this one? So here, to prove this, let us consider let Z is equal to what you have to take the set of elements, say Z belongs to G such that Zx is equal to xz, for all x belongs to G. So this is the center of the group. Center of the group. Let Z. This is capital Z. So capital Z is the set of elements of those elements which commute with each and every element of G. So okay, so now for all x belongs to G. So next, clearly Z is a subgroup. Z is a subgroup of G. Z is a subgroup of G because xy inverse belongs to that one. No need to prove that. So clearly Z is a subgroup of G. Now to show that Z is normal, next to prove Z is normal in G. So what we do, we consider let x belongs to G and small z belongs to capital Z be arbitrary elements. Then x inverse is equal to, this we can write as xz into x inverse, or xz can be written as zx into x inverse. Okay. Now this is equal to, this can be written as z into, now group this one, x into x inverse, or z into x inverse is equal to e, or z into e is z only. So which means that now z belongs to capital Z. So which means that when z belongs to capital Z, z is equal to xz x inverse. It means that xz x inverse also belongs to z. So which means that xz x inverse also belongs to capital Z. So therefore, by the definition of the normal subgroup, okay, Hg inverse belongs to G, then G is a normal subgroup. So therefore, Z is normal in G. Z is normal in G. So this is the proof of the theorem. So with this, I conclude this class and I will continue in the next class. Thank you.